Okay, hello students. I thought we'd investigate one of those challenge problems in Calculus Hybrid today. This was number 68 from section 2.4. It's basically a calculus problem in hiding. The first part is really just an algebra problem, and the second part asks you to do calculus using your calculator instead of actual calculus and exact techniques. So I think the setup of the problem involved a tree and a building, and there was a fence in between the tree and the building. So the task was to first find if there's 63 feet of rope used where you have an attach point at the tree, and then you stick it to the fence, and then you run that up the building, 30 feet up the building, or whatever. The point was in part A, the algebra part, to figure out where you're supposed to attach that to the fence so that that 63 feet remains tight or taut. So that's the first point. There's no maximum or minimum process in this problem to begin with, so that's why it's just algebra and not calculus. Maximizing and minimizing is really a calculus problem. So I just wanted you to attempt this as best you could. The important part about this is really the problem solving, the drawing the picture, and the understanding what you're supposed to do. We're supposed to figure out where this guy is. This could be attached right here and it would go up like that. It could be attached way over there closer to the building and go up like that. There's all kinds of variables. This is variable. This is of course fixed. This is fixed, and the distance between the tree and the building you can't move unless of course you dug up the tree or something silly like that. So we need to attach a variable in order to describe that movable fixed point on the fence. I shouldn't say fixed, that movable point on the fence that we have control over. So I'm just going to call this distance from here to here x. So if I call that x, I think it should be pretty natural that the remaining distance of that 35-foot span from here to here is going to be 35 minus x. Alright, so now we have some variables attached. We also know that this distance is 63. So you could just say that, you could set up what we call in calculus and physics and problem solving in general, an auxiliary equation. You could say, well, I'll just label this length 1 and this length 2, and my auxiliary equation would be length 1 plus length 2 equals 63 feet, because it's fixed at 63. But now you can see how many variables we have. We have an x, we have a length 1, and we have a length 2. So that's 3 variables. We need 3 equations to describe the situation in order to solve for those variables. And really, we just want to solve for x. So let's try to eliminate one right away. This is the mistake I made when helping a couple people this year. And we had about 2 minutes to look at the problem. So I think that you definitely want to try to get rid of one of those variables. And the thing is, you really don't need one of these lengths. Because if the whole thing is 63, just like this whole thing was 35, just like that, you can say, well, then this is 63 minus length 1. Or you could have done it with length 2. What you call your variables is completely entirely up to you. So now we only have 2 variables and we won't need that auxiliary equation. So we're just supposed to solve for x here. So let's see if we can do that. So the most obvious primary equation or relationship in this picture is, of course, Pythagoras, the Pythagorean theorem. So we're going to go a squared plus b squared equals c squared on the first triangle. And then we're going to go a squared, let's see, I'll be consistent, plus b squared equals c squared on the second triangle. So now we have a system of equations. This one has x and L1 as its variables. This one has x and L1 as its variables. Let me write this down here so that we can work with the bigger one. So there's our second equation. Let's clean this up a little bit. So when you have a system of equations, you guys should know a variety of techniques to solve those. You can do elimination, where you try to eliminate a variable. You can do substitution, where you try to find something that is something else and stick it into the other equation. You can do matrices. This is a non-linear system. You can see the squareds. So I think I'm going to try to do substitution. So over here it says L1 squared is this stuff, or I could solve for x squared. Let's just expand this out and see if we can go from there. So 30 squared is 900. plus, need to be real careful here. That's going to be what? Positive x squared for that thing squared. 2 times this is minus 70x. And then this thing squared, I'm going to go to my calculator. That's 1225. Same thing over here, I need to go L1 squared. 2 times that is 126. Oop, negative 126. L1. And then I've got 63 squared, I don't know that either. So my calculator says 3969. And remember, I have my other equation over here, 2 equations, 2 unknowns. I'm going to use this one to stick into that one since that one's so much larger. So let's see. Well, we could do this a variety of different ways. It looks like we could solve for L1 squared and stick that there. And then L1, if that's L1 squared, is going to be that plus or minus. So I can go like this. L1 squared was, let's use color coding. L1 squared from right here is 20 plus x squared. I don't really even need those parentheses, but I can put them there anyway. Minus 126 times the square root of 20 plus x squared. And there we go. So now we've only got x. It's just an equation in terms of x. It's got a radical in it, unfortunately, so it's not just a parabola. But you can pretty much solve it from there. I'll go ahead and do some of this, and we'll see what we get here. So I'm going to grab my calculator, use it to help me a little bit. So 900 plus 1225. I added those together. I'm going to subtract 20. So I'm moving this 20 over here. I'm going to move this number over here. So far on this side I have negative 1864. I'm going to cross out the terms I accounted for. Let's see what else. I have x squared there and x squared there. That'll cancel out. I have minus 70x left here. And I have this radical expression over here. So let's see, let's divide. Now, you know what? I could divide on this side by 126, or I could just square right now. I'm just going to square right now. So let's square 126. I get 15,876 times this thing. Remember, I'm just squaring both sides at this step, so I need to square this out. So 1864 squared. Whoa, getting some big numbers here. I'll erase what I have over here to compensate. Let's see, 3474496. So let's remember that we're squaring at this step. I'll put that on. I've got 2 times this times this. Negative times negative is positive, so that's going to be plus 260960x. And then I've got 70 squared. That should be, let's make sure, 4900. Lots of big numbers, don't want to mess up. 4900 x squared, negative squared is positive. Okay, let's see. So we've got x squared there. We need to distribute. So 15876 times 20. Alright, so we have that number of x squareds over there, this number here, I'm going to subtract that way with everything. So I'm going to get 0 on this side. Let's see, I have 15876 minus 4900. So that's going to be 10976 x squared on that side. Let's cross out what we've accounted for. And then I'm going to say subtract this over there. And I'm going to subtract this really big number over there. So we have 317,520 minus 347,4496. Okay, so now we just have a parabola, and we can solve it by using the quadratic formula or our calculator. Since this is a really ugly parabola, I'm going to try to use my calculator on it. So let's just make sure that we don't erase any of the important parts, and we'll have a look. Okay, 1 second, Kylie. So let's see, 109,676 x squared minus 260,960x is 315,6,976. And I'm going to try a zoom fit. This is a really huge parabola. I don't know how well my calculator is going to handle it. Notice when I did zoom fit, my calculator handled it immediately. So now I just need to find the which one of these is correct. Of course, there's a 0 that's negative. That really isn't going to make sense for a physical dimension on our rope problem. So I'm just going to calculate the other one. Go ahead and go calculate the 0. And there we go. We get a reasonable answer that's within our domain. So I think we're going to get that x equals 6.686. I think the units were feet. So it's 6.68 feet this way. You always got to be careful on problems like this where the reference point is. They could have said away from the building, and I think they did in this case. So if that's away from the building, you have to subtract 35 from 35 to get your answer. So that's where we're going to get 63 feet of rope. Part B asks something different. Let's look at that now. So part B said, find the minimum value for the length of this. So you don't know anymore that this is going to be a fixed 63. So really you're back to the situation where you have a length 1 and a length 2. So you really just need to find a function that represents those two lengths. So I'm just going to have a function like length of x that equals length 1 plus length 2. So we're going to go back and use Pythagoras again. Length 1 is just the square root of this squared plus this squared. So 400 plus x squared, that's length 1. Length 2 is the same kind of thing. It's going to be the square root of 30 squared plus this distance squared. And we're not going to actually do calculus to find the minimum length there. Now we have a function, we can just put it in our calculator and find the minimum on it. So that's all there is. So I'm just going to stick that in and we'll be good to go. Gonna zoom standard this one and just go from there. You could always try a zoom fit again. Zoom standard didn't work. I have some pretty big numbers like 400 and 900. I'm just gonna try zoom fit again and see if that helps. Yes, it definitely does. You can see this is some kind of shape that looks like it has a minimum out that way. So now I just need to use my window and increase the x and decrease the y just a bit, maybe like 40. Try that. And you can clearly see a minimum right there. It's starting to go up again, so I'm going to say minimum. That's on the left. And I have to wait a second here. There, it's on the up part for sure, so let's see, guess somewhere right in the middle, like that. And the calculator takes care of finding the minimum for me. So the distance away from the tree that we want, that'll produce the minimum length of this rope, is going to be 14, looks like exactly 14. And I should write that in a complete sentence. So if we attach the rope 14 feet from the tree, or what is that? 35 minus 14 is 21 feet from the building. We will use the minimum rope length. And when you did this, it's already there. So that's the minimum rope length is right there. It's 61 feet of 61.033 feet. That's as short as we can make this rope and still make it accomplish our goal here. I'll see you next time.